Hey everyone, welcome back to the channel. Let's talk about aliens, or more precisely, the possibility of finding them. In 1961, astronomer Frank Drake formulated an equation to estimate the number of detectable alien civilizations in our galaxy, the Milky Way. The Drake equation grapples with the factors that determine whether we're likely to ever make contact with extraterrestrial life. Could we be on the brink of discovering alien life? What does the Drake equation reveal about our chances? Buckle up, space cadets, as we break down this cosmic equation and explore the mind-boggling possibilities it presents. First up, we've got our asterisk, representing the rate of star formation in our galaxy. Think of it as the cosmic baby boom rate. Every year, new stars are born from collapsing clouds of gas and dust, each a potential solar system in the making. We're looking for stars similar to our own sun, stable, long-lived, and capable of supporting life as we know it. Astronomers estimate that the Milky Way sees the birth of roughly 1 to 7 new stars each year. Over billions of years, this adds up to billions of stars, many of which likely formed planetary systems. Not all stars are created equal. Some burn too hot and fast, others are too small and dim. But even with these limitations, the number of stars suitable for life in our galaxy is staggering. And that's just our galaxy. We're talking about hundreds of billions of stars in the Milky Way alone. Our galaxy is just one among trillions in the observable universe. So while our asterisk might seem like a small number at first glance, it's the foundation upon which the Drake equation builds. It tells us that the raw materials for life are abundant in the cosmos. In the next chapter, we'll explore the next piece of the puzzle. FP, the fraction of those stars that actually have planets. So, we've established that our galaxy is teeming with stars, but what about planets? That's where FP, the fraction of stars that have planetary systems, comes in. For centuries, we could only speculate about the existence of planets beyond our own solar system. Then, in the late 20th century, astronomers started finding them. First, it was a trickle, a few gas giants orbiting pulsars. But as technology advanced, so did our ability to detect exoplanets. The Kepler Space Telescope revolutionized our understanding of exoplanets, discovering thousands of them. What Kepler revealed was astonishing. Planets are not the exception, they're the rule. A significant fraction of stars, perhaps even a majority, have planets orbiting them. The discovery of planets like Kepler 186f and Proxima Centauri b, both potentially Earth-sized and located in their star's habitable zone, has fueled our imagination. With each new discovery, the Drake equation becomes less theoretical and more of a roadmap, guiding us on our quest to find life beyond Earth. The universe is full of surprises, and as we continue to explore, who knows what other planetary wonders await. We've got billions of stars with planets, but not all planets are created equal. Ni is the average number of planets per star that can potentially support life. We're looking for planets in the Goldilocks zone, where liquid water can exist. Liquid water is essential for life as we know it. But the habitable zone isn't the only factor. A planet's size and mass are crucial. Rocky planets like Earth are more likely to harbor life. Scientists estimate there could be tens of billions of potentially habitable planets in our galaxy. In the next chapter, we'll delve into FL, the fraction of habitable planets where life actually appears. Chapter 4, FL, the spark of life. We've arrived at a pivotal point in our cosmic equation FL, the fraction of habitable planets where life actually emerges. While we have a good grasp on the physical laws governing the universe, the origin of life remains one of the biggest unanswered questions in science. Scientists believe that life on Earth likely originated in environments rich in organic molecules. The famous Miller-Urey experiment in the 1950s demonstrated that amino acids, the building blocks of proteins, could be synthesized from inorganic compounds under conditions thought to be present on early Earth. But even if life could emerge on a habitable planet, there's no guarantee that it will. The fact that life exists on Earth suggests that it's at least possible elsewhere. Is life a rare fluke, a cosmic accident, or is life a natural consequence of the laws of physics and chemistry? Every new discovery brings us closer to understanding the origins of life and our place in the cosmos. In the next chapter, we'll explore Phi, the fraction of planets with life where intelligent life evolves. Chapter 5. Phi, the rise of intelligence. We've reached a critical juncture in our exploration of the Drake equation of Phi, the fraction of planets with life where intelligent life evolves. Life on Earth has existed for billions of years, but it took a significant portion of that time for complex multicellular organisms to evolve. And it was only within the last few million years that humans, with our large brains and capacity for abstract thought, language and tool use, emerged. The question is, how often does life, once it gets started, make the leap to intelligence? Some scientists argue that intelligence is favored by natural selection, as it allows organisms to adapt to changing environments and solve complex problems. Others point out that intelligence, as we define it, might not be the only path to evolutionary success. Even if intelligence is a rare outcome, the sheer number of planets with life in the universe suggests that there could still be countless civilizations out there. But how many of these civilizations developed the technology to communicate across interstellar distances? That's the question we'll tackle in the next chapter when we explore FC, the fraction of civilizations that develop detectable technology. For now, let's ponder the implications of Phi. Chapter 6, FC, Beacons in the Cosmos. Now we're dealing with FC, the fraction of intelligent civilizations that develop the technology to communicate across interstellar distances. Imagine a civilization on a distant planet, perhaps one that's been around for millions of years. They might have mastered their own version of physics, developed advanced technologies, and perhaps even figured out how to travel faster than light. But would they be trying to contact us? That's the crux of FC. It's not enough for a civilization to be intelligent. It also needs to have the means and the desire to reach out to the cosmos. Even if a civilization is actively trying to communicate, there's no guarantee that we'll be able to detect their signals. The vast distances between stars mean that signals weaken over time, making them harder to pick out from the background noise of the universe. Despite the challenges, the search for extraterrestrial intelligence, or SETI, is a field brimming with optimism. The discovery of even a single artificial signal from another civilization would be a watershed moment in human history, fundamentally changing our understanding of our place in the universe. Chapter 7, L, the lifespan of civilizations. We've reached the final variable in the Drake equation, L, the length of time a civilization releases detectable signals into space. This factor brings us face to face with the potential fragility of civilizations, including our own. Imagine a civilization that has achieved technological mastery, reaching out to the stars with their messages. How long will they last? Will they succumb to internal strife, environmental collapse, or perhaps even self-destruction through advanced technology? The lifespan of a civilization is perhaps the most uncertain variable in the Drake equation. Some scientists believe that technological civilizations are inherently unstable, prone to self-destruction. Others are more optimistic, arguing that intelligence and technology, if used wisely, can lead to greater cooperation and sustainability. The value of L has profound implications for the Drake equation. A short lifespan for civilizations would mean that the chances of two technological civilizations existing at the same time, let alone communicating with each other, are slim. As we grapple with the challenges facing our own civilization, the question of L takes on a new urgency. Outro, are we alone? A cosmic question for the ages. So there you have it, the Drake equation, a cosmic thought experiment that has captivated astronomers, scientists and dreamers for decades. Whether the number of intelligent civilizations in our galaxy is just one, us, or thousands, this equation has changed how we think about our place in the cosmos. It reminds us that we are part of something much grander than ourselves, a universe brimming with possibilities. Are we alone, or are we just not listening closely enough? The search for extraterrestrial intelligence continues, fueled by our innate curiosity and the profound hope that somewhere out there among the stars, other minds are contemplating the same cosmic questions.